Login accepted.
So I guess we can start. Welcome and join us in our fight against non-optimality of scheduling algorithms. So how artificial intelligence and open source can help us to solve business decision problems. My name is Dupliak. I'm a software quality engineer.
And I'm Geoffrey the Smet. I'm the lead of the Optoplanner project, and so we're both working on that project. Now, just to give you an idea what kind of problems we want to solve, why you're here, the world is full of planning problems. You might not see them, but they're everywhere. And we can solve them better. We can solve them better with better algorithms. And today we're going to go through three different algorithms, show you how they work, how well they do, and how well they scale, right? So, but what could you do with those algorithms? So one of the things you can solve with these algorithms is the vehicle routing problem, where we need to decide which vehicle goes to which location to, for example, do a drop-off of a pickup of, for example, a technician that has to go to locations across the country to perform a certain service. Now, you can see here, we have here three vehicles, four vehicles actually. So the purple vehicle goes to these locations, and we need to decide which vehicle goes to which location, and also in which order do they go to these locations. There's a number of hard constraints and soft constraints. Hard constraints are things like, for example, these vehicles have a capacity, how much they can carry, like 20 tons over here, this green vehicle, and then, of course, when it needs to deliver 10 tons at this location, 3 tons at that location, the sum of that should be less than those 20 tons for the entire trip of that vehicle. We might also have skill requirements. To go to this location, you need to be, for example, have an armed vehicle with an armed driver and so forth. You might also have time windows. To go to this particular customer, to, for example, as a technician to install cable or internet at their homes, you need to be there between 8 and 10 a.m. because that was agreed upon with the customer. You might have soft constraints like optional dependencies, and of course the biggest soft constraint is you want to minimize the total driving time of all of these vehicles. And so this is you can see these kind of planning problems. So you can see it for supermarkets, retail stores, last mile delivery, whether it be something you ordered online or food deliveries. You can see it for buses, airlines, taxis. They're all variations on this with much more constraints, of course. And you can see them with technicians on the road. So for one case, for technicians on the road, when they implemented this for tens of thousands of vehicles, they expected to have a 1% less driving time. And using the technology we're going to show you today, they actually reduced their driving time by 25%. 25% less driving time, that meant for tens of thousands of vehicles, meant more than 10 million kilograms of CO2 emissions per year. And it also meant more than 100 million of cost savings for that company. So solving these problems better, with better algorithms, can really make a big difference, both ecologically as financially, as also service quality and so forth, depending on the use case.
There is maybe some other problems we can solve with that?
Yes, absolutely. For example, also the employee rostering problem. So in the employee rostering problem, we need to assign shifts to employees. So for example, here we have a morning shift from 6 to 2, an afternoon shift from 2 p.m. till 10 p.m., and so a night shift and so forth. So each of these shifts needs to be assigned to one of our 4 employees. These might have different skills. You need to make sure you match skills. So again, there's constraints. You can only do 1 shift per day. Each employee, you need to match the skill requirements of the employee with the shift. And there might be certain employees might not be able to work in the weekend because of their contracts and so forth. And of course, you have soft constraints. Soft constraints like day off requests. That's the biggest one. For example, this particular nurse says, I want to be free on Fridays, so I can go out. Other employees might say, okay, I want to be free on Wednesday afternoon, so I can take care of my grandchildren, and you want to fulfill those wishes as much as possible. And using better algorithms, you can say yes to your to those day off requests half of the time more, which really improves the lives of the employees in these kinds of companies, right? Or organizations or government cases where they might be. So you see this in hospitals, security guards, firms, call centers, police and fire departments. But you see this everywhere where employees are not working 9 to 5. You might see a planning problem like this. And the world is full of these kinds of planning problems. Maintenance scheduling. You know, the escalator you just took, the elevator you might have just taken this morning to get up to this floor needs maintenance. Somebody needs to schedule that, and you can schedule that more efficiently, and basically have the elevator be working better. Court scheduling, job shop scheduling, order picking. The world is full of planning problems. Once you start seeing them, you see them everywhere. Walk through an airport, you're going to see 5 different planning problems if you look out for them. But today we're going to focus on a simple problem, which you might remember from high school, the school timetabling problem.
Yeah, so what the problem is? We need to assign lessons we have for the different slots that we have. So for example, we have a set of lessons like math taught by Turing for the 9th grade, chemistry and French taught by Marie Curie for the 9th and 10th grade, and history taught by Indiana Jones for the 10th grade, right? And we have 2 rooms and 2 time slots. So what we're going to do is to send those data sets to our solver. And then as a result, we expect each lesson to be assigned.
But that doesn't seem too hard, right? I just take those lessons, I just put them in one of those slots, problem solved. What's the difficulty?
Yeah, sure, but let's see what is the problem. So, for example, we will assign lessons in the way like this, and let's try example A. So every lesson is assigned, but what do you think? Is it going to work?
Yeah, clearly not. You're putting French and math in room A at 8:30. You can't do 2 lessons in the same room at the same time. That's a bad idea. This is not a feasible solution.
Yeah, sure. You're right. So this will cause room conflict. So let's consider another example. So here we actually assign every lesson to the empty slot. So everything should go fine. What's wrong?
Yeah, this looks feasible to me. I mean, ship it, we're done. End of presentation?
Yeah, sure. Well, have you even thought about the teachers?
The teachers.
It's a hard job, really.
Yeah, okay. Oh, yes. So chemistry and French are both being taught by Marie Curie, and we're both scheduling those at 9:30.
Oh, yeah.
Yeah, that's
if we go to the teacher's view, we will see that there is a teacher's conflict. So the Marie Curie are going to teach 2 lessons at the same time. Well, it's kind of impossible, right? And this will cause us the teacher conflict, right? So, okay, let's try another one. Let's just switch the history and chemistry, and it will gonna work, right?
So you fooled me once, right? So let's take a closer look. We also have student groups, like 9th grade. So can you show me a view for the student groups?
Oh, sure. Let's check that.
Yeah. So that's not going to work.
Yeah, exactly. You could see that the 9th grade have the same 2 lessons at the same time. Well, they are not going to learn a lot, right? And so we will skip this. We need to avoid this solution, like student group conflict. So what we left?
Yeah, this looks good to me.
This kind of this looks nice because we don't have room conflict there. Yeah. We don't have teacher conflict if you check, and we don't have student group conflict. So this is our feasible solution. This is what we want to achieve, right?
Yeah, exactly.
So what are we going to do right now?
So what we did is we wrote a simple application to see what happens if you have a schedule like this, right? And how does it look like, right? And we're going to press the solve button there and figure out, okay, depending on some algorithms we tried, and we'll try a few, we're going to see how the results look like and see if it's any good, right?
Yeah, nice idea.
Architecture-wise, what we've built is built a Quarkus application. We've exposed the lessons and the time slots and the rooms as a REST service. With JSON, we send them to the client, and we show them in a simple JavaScript UI. We get the information from the database. We put these lessons and these time slots and these rooms in a database. So the database is a source of truth, which you would probably do in a more production environment too. And we just have our solver go into that database and change things. Our algorithms go into that, pick the data from the database, optimize it, and put it back, right?
Oh, okay. So when we will just push the solve button, the UI will send the solve request to the backend. Backend will process it, save the data to the database, and after that we will synchronize client UI with this database and with the solution, right?
Yeah, that's it.
Oh, great.
We just need one more thing. We need to figure out if we have a solution, if it's good or bad, right? So how could we do that?
Well, we can.
No,
yeah.
we need one more thing first.
Yeah,
We need a domain. We need a few domain classes and domain objects, right? So we need a time slot class, which has a day of week, like Monday, Tuesday, Wednesday. We need the time slot class also needs a start time and an end time, like 8:30, 9:30, and so forth, and end time typically an hour later. We need a room class, like room with name, like room A, room B, and room C. And of course, we need a lesson class, which is the lessons we are going to assign to these time slots and rooms. So we have a lesson with a subject like math, French, chemistry, and so forth. A teacher like Marie Curie, Indiana Jones, and a student group like 9th grade, 10th grade. This is a simple demo application, so we've just used a string for a teacher, but in a more complex application, we would create a teacher object probably with some preferences on when they want to teach and so forth. But that's a bit too complex for today. And then, of course, we have those two fields here, the time slot field. Every lesson needs to be assigned to a time slot. Every lesson needs to be assigned to a room. And they will start out as none assigned, as null. And after our algorithms do what they do, these things will be assigned. So
yeah, all right. All right, so we are going to juggling a bit with time slot and room and have a set of array or set of lesson with assigned time slot and rooms.
Yes.
Yeah, but we need
to score them. So how do you score them?
Yeah. We need to evaluate the solution, right? So to distinguish the bad one from the good one. So let's consider some simple function to do that. So we will use something like score calculation. So to evaluate like a teacher, well, this is a bad solution or not. So we will pass the timetable state to this function, and it will go lesson by lesson and check if these two lessons have the same room, or like at the same time. We will penalize it. Yeah, sure. The same teacher with the same time slot, we will penalize it as well, and the same student group with the same time slot. Yeah. Penalize it. Penalize. Yeah.
So if the score is negative, if the score is not 0, if the score is below 0, we have a bad solution, basically.
Yeah, right.
Yeah.
That's true.
And this is just the hard constraints. In a real application, you would also have soft constraints, which would make this a little bit more complex, but we're just going to focus on hard constraints today. So
we can evaluate our solution, but we need some kind of way to search for that.
Yeah, and I have a brilliant idea. It's called the greedy algorithm. Let me just show you how it works. We're going to use this. It's going to solve everything, right? So the greedy algorithm works like this.
Oh.
We're going to take those. We're going to just take one of the lessons. Let's say the math lesson. And we'll try to put it in each of the possible positions we can put it. So we could put math in room A, 8:30, or in room B at 8:30, or room A at 9:30, and so forth. We're going to evaluate each of these solutions. We're going to take the best one of those. Very simple. The first one, no hard constraints broken. We'll just use this, right?
Okay.
Okay. Then we take the next lesson, history. Same thing. We're going to try it in every position. But now math is already fixed, so we're not touching math anymore. And so you can clearly see if we put math and history in, if you put history in room A at 8:30, it clashes. It has a room conflict with math, so we're not going to do that. So clearly, the second choice is the best one, and we continue from there.
Are you sure about this? This is.
Yeah, no hard constraints broken. Math and history do not share any students. Do not share any teacher. No problem.
Yeah. Okay.
Yeah. Well, I'm pretty sure this algorithm is fine. So what we do is we just continue like this. We take chemistry. For chemistry, that does have the same students as math, so we'll have to watch out for that. But clearly, the first two solutions are bad, and then the third one over here, chemistry is not at the same time as math, so everything is fine, and no room conflicts. We just take that one, we continue. Now we do, for French, it's quite easily, because we only have one spot left over here, right? So those three don't work, we just put in the last spot. We're done. The greedy algorithm works. Thanks for listening.
Well, don't you spoil spot anything there? Well, actually, the chemistry in French is taught by Marie Curie, right? So, well, we have broken the hard constraint here.
Yeah. And Marie Curie probably also should teach Polish, right? She was originally Polish, but she also could speak French, so this does work, right?
All right, yeah. So, and the worst part is that this solution was already doomed on the second step, because we were not going to get the feasible solution already making the history, putting the history to the room B. So even though we're picking up the best solution on each step, we are not falling to the feasible one.
Yeah, but can you show us how this works? Can you show Can you show how this code would look like and do a demo of that?
Sure. It's pretty straightforward. So we just go lesson by lesson and assign time slot and room and calculate the score. And if the score is better than what we got before, then we just pick up the solution. That's it.
So we and so we only have one lesson at a time, right? That's the big trick here, right?
That's a big trick.
Yeah. Okay. There's a lot of things. Yeah, makes sense. Can you show us how this works?
Yeah, sure. Why not? So I prepared the repository for that, and let me just. Okay. Yeah, I'm here.
Yeah, and that's the wrong directory, right?
Okay. Yeah. Let's go for it.
We're in the root directory, I think.
Oh, okay. Doesn't matter. Greedy. Great. So.
Yeah,
that's nice.
So this is another.
Yeah. All right. So we will run this application within the development mode. Yeah. So let's see what we have here. So the backend is ready. So you could see here exactly this set of lessons that we were considering. So just, let's launch it. So what do you have here? All right. So we have a solution, but the score is -1. Is the hard score broken? So one of the rules went wrong, right? So let's see the teacher's view. Yeah, exactly. So the chemistry and French was set to the same time slot. We don't want it, but there is no way how greedy can come over that. Yeah. So let's check for consistency. The student group is okay.
So this is for 4 lessons, right? Can you crank it up to 20 lessons or something like that?
Yeah, sure. Let's experiment with that. For to doing that, I need to go for the resources and change the application properties like this. And then we will increase the amount of lessons. And since we are in the live mode, it will update the data directly. And so now we have 20 lessons ready to be assigned. And if I push this all button, it's pretty much simple and quick. Yep. And we have, again, a lot of lessons assigned, but the score is -1.
Yeah. Okay. And is it again with the teachers or?
Let's check it.
I think it's with the student groups.
Teachers is okay, but.
Yeah. Okay. We're asking the students to be in 2 places at the same time. Yeah. So so maybe my idea with greedy wasn't that perfect, right? So.
Yep. So, what about the other idea? How about using the something else?
Yeah, greedy was fast, not optimal. Do you have a better idea?
Yeah. Well, how about brute force?
Okay.
Yeah. All right. So the brute force idea, you're pretty much familiar. Every of you. Well, we just pick up every combination and try it out, right? And the timetabling problem looks not that hard to solve. So we will assign the math. For each math, we will assign the history, etc., etc. And by plan, we will have a feasible solution in a reasonable time. Yeah, right. And the brute force short pseudocode is here. So for each for each lesson, we will create the combination of this room and time slot, etc., etc., and again calculate the best score and pick up the best solution based on that.
That looks like a lot of nested loops, though, where for loop for one lesson, two for loops for one lesson, two for loops for the next lesson, and so forth until we had the end lesson. And you can't really code it like this, right? I have n lessons.
Oh.
Yeah.
Yeah, we just will need to generate it dynamically. It's not a problem, right?
Yeah.
So, yeah, that was a pseudocode, and real code is a bit more complicated, and you could find it in the repository. We will share the link with you after the presentation. So let me then go a bit.
Yeah, so if you want to download any of these codes, you will find them in the repository. We'll share the link. You can try any of those. So we have the greedy implementation, you have the brute force, and as you can kind of guess, there's a third implementation waiting later during the presentation.
Okay, so let's check it.
Yeah.
The brute force, it's nice.
Okay.
All right, and I just push the solve button. And we are done.
Yeah, and that looks optimal. Can you show student groups and teachers?
Yeah, score is 0, but...
Yeah, I always like to see the schedule. You never know, right?
Okay, yeah.
Seeing is believing.
All teacher is fine, student group is fine, everything is fine, we're done.
Yeah, but I'm worried about those nested loops. Oh, thank you. I'm worried about those nested loops, though. Can you try 20?
20? Okay, 20, no problem. Okay. Brute force timetabling, SRC, resources, application properties, again.
Anybody have an idea what will happen? Yeah.
No, everything will work fine, just fine.
Don't spoil it.
Okay, 20 lessons, let's go.
So this is the solve. So what's going on? What's going on?
Yeah, it's just working. Everything is fine. You don't see the solution while, but
We just have to wait a little bit, right? Just wait a little bit for the solution.
Yeah,
for this.
a little bit.
A little bit. So so what's the problem, right? The problem with brute force is if you look at the number of nodes we have, on the top node there, just assign this one math lesson to those 4 slots, that's actually 4 nodes, right? And if you then go down one level deeper, you actually have, where we try every possible position for both history and math, you have 4 times 4 nodes. That's 4 squared. When you then try it for 3 lessons, you get 4 times 4 times 4, or 4 to the power 3, right? And if you have 4 lessons, that's 4 to the power 4, right? And you might say, okay, that's still only 256 nodes, so what's the problem? But if you actually look at it at the grounder scale, it means if you have n lessons, you have n to the power n nodes. So if the search space, the number of nodes you need to look at, and for every one of these nodes you need to calculate the score, is for 400 lessons, which is very normal for normal high school. Every group of students has 40 lessons a week, right? That means we only have 10 groups of students, which is a very small high school, right? We already have a search space of 10 to the power 1040.
Oh, that's like a gas prices right now, right?
Yeah, it's a little bit like gas prices these days, but it's a little bit worse. But because if you compare it to the number of atoms in the observable universe, right, that's only 10 to the power 80, and this is much, much bigger.
Okay.
So, so how long will it take to solve our problem, right? So for brute force, we try this out, and you can try this out with the code yourself. To solve 4 lessons and assign it to 4 slots, that's 8 milliseconds, right? 5 lessons, 0.1 second. 6 lessons, 2 seconds. 7 lessons, almost 3 minutes, right? And then it comes, right?
Okay.
The wall, right? 8 lessons, 1 hour. 9 lessons, 1 day. 10 lessons, 1 month. 13 lessons, 2,000 years. That's when Voyager 1 will pass the first nearby star. 15 lessons, 2 million years. That's when the Apollo footprint will fade on the moon. So 17 lessons, 5 billion years before this method would return for us, and that's when our sun explodes.
Right, I don't need a timetable for it.
Yeah. do we want to wait for 20 lessons, or do we want to kill it?
Kill it with fire. All right, let's kill it. It's brute force or brutal solution.
Yeah.
All right.
So if you look at brute force, it's not optimal, right? It is optimal. It's perfect.
Yeah, it's perfect.
Yeah, but it doesn't scale, so you cannot use it. It's never ever useful, right? So let's try something else.
Yeah. Well, do we have something?
Yes, of course, because we're working on a product that solves problems like this, an open source project, of course. So let me just first explain the algorithms behind it. There's a whole bunch of these. They're called meta-heuristics. In meta-heuristics, you have a number of subsets, and one subset is the local search algorithms. And within those, you have a number of subsets, such as, which you might know, similar to annealing, taboo search, and the newer one that is really nice is late acceptance. But we're just going to explain the general concept behind these. So for local search works like this. We first run that greedy algorithm, the one we showed first. That was actually very fast to get an initial solution, right? So we're going to take that initial solution where you see there's between chemistry and French, there's a problem, the same teacher. And we're then going to make changes on this. Most simple form of local search works like this. What you do is you take, for example, the math lesson over here, and you just move it to one down, or you move it to one to the right, or you move it to any of the other positions, and you do that with any of the other lessons. And you create what we call moves, and there's many of these, and you subsam with some smart algorithms and certain methods. You select some of these to actually evaluate, and the ones you evaluate, the one that works best, you might or might not take. If it improves the solution, you take it. If it doesn't, there's again a whole bunch of algorithms to decide when and when you don't. But in this case, we'll just take that one because it does worsen the solution, or it actually doesn't worsen the solution, but doesn't make it better. Actually, it does worse because we have 2 lessons at the same time in the same room, and we also have, as you can see here clearly, so history and French are taught both by. It's just 2 lessons in the same time problem, right? So we continue from that, and for example, if in the next we try a number of moves, and if in this one we would actually decide to move then history down and French up, then we would actually find the optimal solution. And that's how local search more or less does it. There's much more complexity behind this. Unfortunately, our presentation isn't long enough to go through this. But of course, we offer our open source library called OptoPlanner, which is a library of solving algorithms, and it has all of these algorithms to work for you to solve this for example, in Java or Kotlin and so forth, right?
Okay. Can I freely use it?
Yeah, it's Apache license, right?
Okay.
So you can use it anywhere. You can do with what you want with it. It's all Apache license. And like I said, you can use it in Java. It's completely written in Java. We have multiple examples in Java, for example, the vehicle routing, the maintenance scheduling, and so forth, the employee rostering. You can find this in our quick starts repository. And we also have an example fully in Kotlin. So you can write it from Kotlin, you can fully use it too. It works in plain Java. When you have for example, you add a jar to your class path and you just use it. But we have extensions for both Quarkus and Spring, which make it faster and so forth. That's the Quarkus extension is the one we were showing earlier. All of our examples, all of our quick starts use Maven, and 3 of them also show you how to do it in Gradle. So the Quarkus one, the Spring one, and the Hello World one have a Gradle build too if you want to use it from Gradle and you want to see how we did it. But it's just a jar on Maven Central, so it doesn't really matter that much. If you're in Python world, we have a Python wrapper these days called OptoPy, which you can just pip install. It's Java, so it works on all operating systems, works on all clouds, works really well on Kubernetes and OpenShift, but really just works on this laptop well, as you can see too. I even have a version of it running on my mobile phone. So, but that required a bit of tinkering though.
Should I change a lot in my application architecture?
That's a good question. So So first of all, if you use the Quarkus platform, you just add the Quarkus extension, right? So you get OptoPlanner. You just click that in code.quarkus.io, and you have that one too. And then what you need to do indeed is you take your domain objects, right? So the ones we already showed earlier, that lesson class, the time slot class, and the rooms class. OptoPlanner needs to know what it can change for you. So you need to tell him that I want OptoPlanner to fill in, I want OptoPlanner to assign the lessons to a time slot and the room.
How to do that?
Well, we just annotate those two things we can change, the time slot and the room at the planning variable. So then OptoPlanner knows these are the fields I can change. So it's not going to try to change the subject or the teacher of a lesson. That would be very bad, right? You want to really limit the amount of decisions it can make. So you say, okay, time slot and rooms, those are the planning variables, those are the things you can change. And the class where this contains these planning variables, that's called the planning entity class. And so that's the one that changes during planning.
Yeah, okay, so now we can juggling, and OptoPlanner knows how to do that. What can we touch or recombinate, etc. But how can we use this? Evaluate our solution in OptoPlanner.
How would we do this score? Well, there's several ways, and the easiest way is called the easy score calculator. And if you look at this code, it's exactly the same code we showed earlier with two changes. Like the return type is not an int, but a hard soft score. And of course we return not just the hard soft score as an int, but we return it as we create a score object with it. These score objects are immutable, are just things that are comparable. Why do we have a hard soft score? Because you might also have soft constraints, and then you have two numbers, and you want to have something to wrap those two numbers, so a hard and soft score. Now, we do actually have other score implementations, such as hard, medium, soft score. If you have three numbers you need to take into account. And the thing between hard and soft scores is quite simple. One hard score is worth more than an infinite amount of soft scores, right? So then more than, let's say, 2 million soft scores, 2 billion soft scores. One hard score is worse. You always want to focus on the hard constraints first. So let's do a demo.
All right, yeah.
Okay, and some live coding just to make it interesting, so things can go wrong. So I'm going to go into the OptoPlanner directory. So here we go, and I'm going to go in here. So let me just. So what I've done here is we have that easy score calculator I talked about earlier. The code is a little bit longer. I am doing something we should have done actually in the slide too, not just for this implementation, but also for the original greedy implementation. And we have that actually in the implementations there, is that if the lessons are the same lessons, we break out, because we don't want to inflict hard constraints when the lesson is compared with itself. But beyond that, it's the same thing. We just say, okay, same room, same time slots, we break the room conflict, and so forth, right?
So if I compare the same lessons, I will not have like score 2 instead of score 1, right?
Yes.
Okay.
So okay, let's run this.
Reasonable.
So we're going to do Maven Quarkus dev, and let's see if it solves it. All right. So we're just for the record, I've immediately put this one on 20 lessons, as you can see. So we're immediately trying the one that with greedy did not give us a feasible solution, and with brute force will give us a feasible solution if we wait a couple of billions of years or something like that.
Yeah.
So let's try that out. Here we go. Let's solve. So these are the 20 lessons at the bottom. You can see it finds a solution, and it's 0 hard, 0 soft, just to show seeing is believing always, right? So the teachers. So this looks good feasible-wise, right? So the teachers can go to all of their lessons, the students can go to all of their lessons. But you can also clearly see already that the teachers here, they might not like this schedule. There's gaps in between. And that's when soft constraints come in. So if you look at the full example, which is available in the repository, you'll see that we can easily add a soft constraint here to make sure that the teachers get compact schedules, which means that they don't have these gap hours, or they can, they do all of their lessons on the same day or in a row, right? Like these gap hours are really annoying for them. They lose a lot of time for that. They have to come to the school, a lot of commute, bad for the, more commute is also bad, right?
Yeah, those teachers actually occupied, and don't have time.
Yeah. So if we now I promised some live coding, right? So what's the problem with this thing? So can anybody think of the problem with this easy score calculator? Well, if we look at it, let's crank it up a bit. So let's go to do 100 lessons. All right. Here we go. And we refresh this. This is Quarkus dev, so we just refresh and we immediately see the results. We change something, code, we immediately see the results. So when we solve this one, what you'll see is it took longer, right? And that's because it's using that easy score calculator. It does reach 0 hard and 0 soft. This is 100 lessons. There's now more student groups, as you can see. There's now 4 student groups and so forth. But if you look at the amount of time it took to solve that, you'll see that the construction heuristic only, so that greedy algorithm took 5 seconds, and to get to that optimal solution there, it takes some time. And this is all because of it doesn't scale well because of this code. This code does not scale well. So what's the problem with it? Well, there's a couple of problems. First of all, we could use hashing here between these things. Instead of going through every lesson with every other lesson, if you just put them in hash maps, then we could say, okay, I have a hash map where the key is the room, and then the value is the list of lessons. So that's one thing. You could hashing and database indexing techniques that would really speed things up. But that's not really a big gain. That's a small gain. That will get you maybe 10 times faster or something like that. That's a small gain. The big gain is doing this incrementally. Every time Optoplanner looks at a new solution, it changes 1 or 2 lessons. Why are we recalculating all of the other lessons? When we change, for example, math, why are we doing a for loop that checks if French and chemistry are in the same time slot? Right? We didn't touch math and chemistry. If they were still, if the hard constraint was broken in the previous solution, right, it still is. If it wasn't, it still isn't, right? So we need to do this incrementally. Now, writing incremental code with deltas and so forth is extremely, extremely difficult. Can easily make you insane.
Oh, so it's another bench of fors and ifs or something?
Yeah, and and then you need to listen to the events. Like this has been changed, and you only change the delta of the score based upon it. You don't want to do that. We have an interface if you do want to do that. We have examples in upstream where you can look at how to do that. You don't want to maintain that code, and you definitely it's not nice to the next person inheriting this code to use that. So what we're going to use instead is our constraint provider API, which is a functional API. And what I'm going to do is I'm going to delete our easy score calculator. I'm going to switch to this, and I'm going to here say, okay, I'm going to implement the constraint provider. And here we go, constraint provider class. And this is a class which has a single, this is an interface which has a single method which needs to return us the constraints. So let's say for now we return an empty array. We say we don't have any constraints, right? Easy. And so this is Quarkus, so we can just jump here, refresh. This is with 100 lessons, so that's really going to end badly. But what you can see here quite clearly is we're putting all of the 100 lessons in room A at 8:30 if we scroll down enough. So that's not...
But it's okay, because we didn't do any constraints yet, right?
Yeah. So let's add a constraint. So
about the rooms, maybe?
Yeah, let's start with that one. So I'm going to add a room conflict constraint. I'm going to say, okay, I want a constraint. I'm going to create a room conflict method, which returns the constraint. So I'm going to say, okay, constraint factory. I'm going to build a constraint, and I'm going to say, I'm going to check for each lesson. So this is a functional API. And I'm going to join that with each lesson. That's basically, it's a little bit similar like doing for each lesson with, and then nested with for each lesson again. But it will do the changes incrementally. And then I'm going to check, okay, are these, do those 2 lessons have the same room or not? So I'm going to check, okay, I'm going to say equal room. So let's do lesson get room. Okay, let's import this joiner. And I'm also going to check, of course, they don't just need to be in the same room. They can be in the same room, 2 lessons. But they need to be in the same time slot, of course, right? Not just in the same room. So here we go, same time slot. And if that happens, I'm just going to penalize this as a room conflict. The nice thing is by giving this a name, we can then ask Optaplanner later, okay, why does it have this score? And it can actually justify that, but that's a more advanced use case. And then we're going to say, okay, we're going to do of heart 1. This is 1 heart score we lose for that. Every time we have 2 lessons in the same room at the same time, we lose 1 heart point. We're going to hit Optaplanner on the head, and to avoid it doing that.
Yeah, this look like some SQL statement that you just filter the solution and penalize those that are not.
Yeah. And apparently live coding is always fun. I'm missing a return statement, so that's always fun. So let's do that. Here we go. This will work better. Interesting enough, during our preparations, we tried it with 20 lessons, not 100. So this is a bit scary. So it works. We don't have any room conflicts, as you can see. We do still have a bunch of problems with the teachers and with the student groups, I presume. Yes, we do. But we are still seeing 100 hard scores broken. So let's fix that one first. So what we can do here is the problem is the same lesson is actually being compared with the same lesson. And then, of course, it's the same room and same time slot.
Okay, yeah.
So we'll just throw a filter in there. And we'll just say, OK, lesson 1, lesson 2. Here we go, and I want to make sure that lesson 1 is different from lesson 2. Here we go. So let's try that out. See if we can get rid of this 100 score there. Let's solve that. And here we go, 0 heart, right? Still bad for student groups and teachers, but good.
We didn't define it.
Yeah, okay. So
let's define it.
Yeah, let's define those. Let's do the teacher one. So I can actually it's pretty much the same code, right? So I can just say, okay, I'll take this code here, and I'll duplicate that. I'll call this the teacher conflict, all right? I'll throw this in here. Let's do a teacher conflict. And I'm going to say, okay, for each lesson, join that with every other lesson. So now we have a pair of lessons. If they are not the same room, but the same teacher, get teacher, all right? At the same time, then we are asking this teacher to be in 2 places at the same time. If they're, of course, different lessons, then we have a teacher conflict. We'll make it a hard constraint. Okay, let's try that out. Here we go. Here we go. And that looks good room-wise. That looks good teacher-wise. See, no teacher conflicts. We're not asking Marie Curie or anybody else to be in 2 places at the same time. But still bad student group-wise, so let's fix that too. Same thing there. I'll just copy this once more. Call this the student group conflict. Check if we have 2 student groups in the same time slot at the same time. Student group conflict, and throw that in there. And then, of course, if you would do this for real, you would add a bunch of soft constraints, like making sure that the teachers have a compact schedule, making sure that the students don't have 3 lessons of math or anything else after each other. You would add and any other soft constraint you can think of, fairness in the distribution. For example, if there's a teacher that says, I don't want to do morning lessons, right, because they hate mornings, you can actually take that into account and say, okay, we're not going to give that teacher morning lessons. But anyway, we're solving it now for 100 lessons. You can see it's good room-wise, teacher-wise, and now also student group-wise. So you might say, okay, and if you do this manually, remember when your high school did this, when you were still going to school, this could take weeks to come up with a schedule like this, right? Because it's extremely difficult. It's very easy to do the room size one, but it's hard to do the student and teacher group side one. So Optaplanner, open source Apache licensed library. You just use it. It's fast. It's scalable. These algorithms, or you write those algorithms yourself, and that took us a few years. And and it's near optimal, right?
All right. So so in the end, we got this. So the greedy algorithm is fast and scalable. We cannot achieve our feasible solution. The brute force will give it to us, but it's really cannot do that in time. So well, meta heuristics we have so that it's fast, it's scalable, near optimal. That's enough for us.
Yeah. And yeah, how did you get started?
Yeah, so to get started, just try. You could use the QR code and clone the repository and build it with Quarkus Dev in dev mode and try it yourself. Please do that and make make it yourself, and that's wonderful. All right.
Yeah.
So we have some time for questions.
Yeah,
And
we have 3 minutes for questions. Yes? Yes?
oh wow.
The first one is, can I add the inputs to the Okta planner from other sources than the databases, like everything, the code or JSON or something like that?
Yeah,
Okay.
so the question is, can we get our data from other places than a database? And the question is most definitely yes, right?
All right.
We don't care. It's domain. You get Java domain objects. We don't care if they come from JPA, from a database, or you get them from MongoDB, or you get them from a REST service. They come from an ActiveMQ. We don't care. It's just plain old domain objects. And we give them back to you, and you do whatever with them what you want. We have one of our examples uses ActiveMQ, for example, so gets it from with a JSON thing from ActiveMQ. Most of our examples do database because it's what many people use.
Yes, in this example, we were using generator, but in the quick starts, you will find the presets, and in examples in the Optoplanner core, you will find some XML prepared data.
Yeah.
So
Let's switch questions just for fairness sake. Go ahead. Oh, I started as a hobby project 16 years ago because I wanted to and had an idea. But nowadays, we work for Red Hat, and it's used all across the globe for all kinds of planning problems. And people find new usages every day, right? There's no really an original need. And that was a question, by the way, for the recording. Yeah. Yeah. So the question is the solution always the same? So are we reproducible?
yeah, we can. We can. Yeah, we are reproducible. So you could do that.
So if you run for the same amount of, let's say, CPU time, you will get the exact same solution. You can even do a termination, say, I want to stop after this many iterations, and then you will get guaranteed the same solution. Even if you do multi-threaded solving. So we have something called multi-threaded solving, uses multiple threads, all kind of stuff, and we still guarantee you that you will get something. Let's say you're a bank and you want to say, I want to run 5 years later, the same calculation with the same code, you will get the same results. However, if you say, I want to run for 5 minutes, then it depends on how much CPU the thing gets. You will get the same solutions in the same order, but it might stop one solution earlier or later, and that might give you a different solution with a better score. Right? It will always give you the best score it found at that point. Yes, let's switch again because we had one more there.
So I know that these type of problems are called integral programming problems. Do you say that Okta Planet is a general integral programming solver?
Yeah.
And I'm asking this question because I want to understand if I can use Okta Planet for any.
That's a very good question.
Or do you have only a subset of solvers?
Yeah. So the question is this integer programming? And the short answer, these kinds of use cases are mixed integer programming use cases. So we're not using linear programming to solve them. We're using meta-heuristics, as you've seen also. We have a few other algorithms behind those, besides those two. And what you will see is if you want to solve vehicle routing problem and those kind of use cases, that the best algorithms on the world are meta-heuristics. They always win the competitions. They beat any linear programming does not scale, for example, for vehicle routing. On the other hand, if you have other kinds of problems, like, for example, deciding how much percentage of, when you want to make toothpaste and you want to decide how much percentage of ingredient A versus ingredient B and so forth, that's non-discrete. You can take any amount of percentage that's continuous, and that's where you'll find that OptaPlanner is not the right tool for the job. So it depends on the use case. So if you see it in our examples list, it's definitely a good use case. And there's a whole bunch, of course, we don't have examples for yet that work. But it depends on the use case. There's not one tool that solves them all, to put it like this. Yeah, but for example, if you do that for the toothpaste problem, it's not going to work that well as linear program, and vice versa. If you do vehicle routing with linear program solvers, that's a disaster. So yeah, yeah.
So would you have like benchmarks like how the solving time increases when you keep adding constraints?
Yes, we have something called the benchmark. So the question is, do you have? So if you add constraints, how does it affect the runtime and so forth? Yeah. 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 So we have something called OptaPlanner benchmarker. I think we might be able to show it. I have it somewhere. Let me just check. So these are old benchmarks, but we have some. We have this. It's also open source Apache, of course. This thing you should. All of our users should be using this. Less than 5% are, and so it's our mission to tell everybody about this. And what this basically does is it shows you per solver, per algorithm, how good it is. So you can see here the different algorithms on different use cases. These are different sizes, and then you can see how it scales out, how it will behave when you increase constraints, and so forth, and so forth, and so forth.
Yeah, you can find it in the OptaPlanner core, an OptaPlanner repository.
Yeah.
Well, unfortunately, we are out of time.
Yep.
So if you have another questions, just come to us, and we are waiting for you.
Okay. What happens if the constraints are in contradiction? There's two options. Yeah. So there's two options. So first of all, the amount of time you give it, that's the amount of solves, right? But if you have constraints that are in contradiction, so there's no feasible solution, you will get the least infeasible solution. Like you will get the least amount of hard constraints broken. If you don't want that, because often you don't want that, you can do something called over-constraint planning, where you say don't assign lessons if you can't assign them without. So find the least amount of lessons not to assign, so you do get a feasible solution. And so that's called over-constraint planning, a very advanced use case, but we do this very often. So we do have solutions for that, and it's all explained in the manual.
We have another question.
That's. Oh yeah. We have to give up the hat, right?
All right.
So let's get. Anybody want a hat?
I guess we can give for questions.
Oh, that was sounds good.
That's unfair. Yeah.
Okay.
So please come to us and for another hats and questions as well. Thank you very much for coming.